We're going to complete this chapter by talking about reflection, transmission, and refraction of waves. So consider you have this rope that is a light rope, but then in the middle you have, I don't know, something wound around it so it becomes a heavier rope. Well, what happens is that lighter section hits the denser medium. Part of this wave will actually be transmitted forward. In other words, the energy of that wave will be transmitted forward. But not all of that energy will move forward. Some of that energy will actually be reflected backward and will form a reflected pulse moving back the way it came. So here in this video, we're going to talk about some reflected waves and then some transmitted or refracted waves. Now, we can demonstrate 2 or 3-dimensional waves in different ways. We can use either wave fronts or we can use wave rays. Let me show you the difference here. Here in this module, let me navigate to that for you. We're showing, well, right now it's showing 2 balls that are oscillating up and down, creating waves in the water. Now, I'm going to get rid of the second one. I'm just going to bring them together until they're basically one. This problem here is actually a really cool one, and we will discuss that in a future chapter, in chapter 24. But we're just going to deal with one here. You notice how it creates waves, and those waves are a series of crests and troughs that move out. Well, all we have to do is draw a line on top of each crest. If you draw a line on top of each crest, then that is a good way to represent wave fronts. So, as a result, when we draw waves on paper, this is what we can do. We can either draw these blue lines, which depict the crests of the waves moving in its forward direction. And this is the typical way that we draw waves using the wave fronts. But sometimes, like when we talk about optics in chapter 23, it's also useful to depict the direction that the wave is going. And so we draw these vectors that are perpendicular to the wavefront, showing the direction that they are moving. Notice that these wave rays are always perpendicular to the wavefronts themselves. Now, there are 2 important laws of waves that we want to talk about that we introduced at the beginning of this video: reflection and transmission, or reflection and refraction. Let's talk first about the law of reflection. That is that the angle of incidence, in other words, the angle of an incoming wave or ray, is going to equal the angle of reflection. So here we have, let me get a different, adjust my pen a little bit here. There we go. Here you have a wave ray that is coming in, and it hits the ground at a particular angle. Using wave fronts, you can measure the angle from the wavefront to the surface. However, that's usually not the angle we measure. Usually what we do is we take the incident ray and then draw a line that is perpendicular to the surface. We call this a normal line. Let me pull that up. This is our normal line. And then we measure the angle from the normal line to the ray. And that's how we measure the angle of waves. So we've got our incident wave, and it comes in at an angle of theta I being incident or incoming. And then it reflects, and as it does so, it's going to look something like this at an angle theta r. In other words, reflected angle. Now, the important point that we need to make from the law of reflection is that the angle of incidence equals the angle of reflection. So theta I is equal to theta r. The incident angle equals the reflected angle. Another important law we need to talk about is refraction. Now, when light hits a reflective surface, then you follow the law of reflection. But what if you hit another medium where the wave actually moves into the medium? For example, you may have water that's moving in the ocean. And let me be consistent and use my incident as yellow. And then you move into water that has a different density, or you move into a region where you have more of an obstruction. Basically, the motion of the wave has to change. Well, what happens is that this wave will slow down, and because it slows down, it also changes direction. This is easily seen using the waveguides, or the rays. The light is coming in at some angle theta I, but after it hits the medium, all of a sudden it bends and is now moving in a slightly different direction, theta r for refracted wave in this case. Okay. Now we can find an easy relationship between the two, and we find that using a little bit of trigonometry. I will move to this slide and then I'll come right back. So you can use some trigonometry here. This figure is in your textbook. Using trigonometry and similar triangles, there's one triangle and here's a second triangle. Using a little bit of trigonometry, you can come out to this equation, which is that the sine of the refracted ray divided by the sine of the incident ray has to equal the refracted wave velocity divided by the incident wave velocity. Here's an interesting way a second way I'd like to depict the refracted waves. Imagine that you have you're watching a parade, and this parade you have a bunch of soldiers, and all those soldiers, let me grab a highlighter instead. All those soldiers are in a straight line, straighter than what I can draw apparently. That's still not very good. Anyway, they're in a straight line, but on dry ground they're in a straight line, but then one end actually hits a muddy area. And then because they hit a muddy area, they have to slow down. So the rest of the line keeps going, but the soldiers that are moving into a muddy area have to slow down. And so in order to stay in a straight line, they have to move at a slightly different angle. So that's another way to think about the difference between incident and refracted waves. In fact, that very example is actually used in your textbook. The last point I want to make about refracted waves is that it goes both ways. You can either have refraction happening with the incident ray coming in and then bending at a refracted angle, or you can have it coming from that second medium, hitting the surface, and then it'll refract at that same, basically it's a reversible process. If you have light going in at one point, it'll refract, and if you have that light reflect right back along the same path, it goes both ways. Yeah, those words kind of got away from me. It's a reversible process, goes both ways. A wave going from a slower medium into a faster one would follow the same red lines in the other direction, going from the faster medium to the slower medium. So it's a reversible thing.